All right, guys, getting into our final section of Chapter 6. We're going to break this one up over into 2 lessons, so this is part 1. So we're going to first just remind you of something that you guys learned in Algebra 2, which gets into the complex number system, mainly this guy right here. Right? So we worked in Algebra 2 to look at how do we deal with negative even roots in such a way that we can continue working with a process instead of just kind of saying that sort of no solution type answer. And so what we developed was anytime we have the square root of a negative value, we can replace that negative with the letter I. Right? And so this represents the imaginary or a complex number that really couldn't be worked with otherwise. So we replace it with a variable, so it allows us to continue on with a process. So as you look at this one, just remember that the square root of negative 1 is I. Within the complex plane, your x-axis is the real axis. So as we go to the left or the right, we're talking about a real number. And then if you're going up or down, we are talking about the imaginary value. So let me show you a quick example of that from your textbook. And again, this is something you would have done in Algebra 2 if it lets me scroll down. There we go. So as you look at this, again, this is your real axis. This is your imaginary axis. So if you look at the little setup that you see right here, a plus bi, a represents a real number, and b represents the complex or imaginary number. So whatever that real number is, that's how far we would be going to the left or right. Whatever the imaginary number is, that's the y-axis, that's how far you go up or down. So if you took a value like, and I'll just grab one here, so what if we said 1 plus 3i? All right, so if you looked at that one right there, that would tell me that I'm going to go 1 to the right, that's my real value on the x-axis, and then I would go up 3 on the imaginary axis as my y-coordinate. So real simple. Just wanted to remind you of what that stuff looked like. It's been a little while since we've seen those. Definite connection to vectors that these guys have, so that's one of the reasons why they fit into this chapter, as well as continuing on with some of our trig and polar form processes as we look at these guys. So let me continue onward for you. So the absolute value, or here's a new vocab word for you, the modulus of a complex number, which looks like this. Right, and so this formula should look real familiar to you. It's what we've already been looking at this chapter, and of course, just as directly goes back to Pythagorean theorem. Right, as we kind of can always make that connection to these right triangles by whatever you go to the right, and then whatever you go up is going to form that right angle that we see right here. So this is like the basis of all that trig stuff that we've been doing for the last couple chapters. Is all based on these right triangles. So just see the connection on this that. If this is what I'm going to the right and this is what I'm going up, those represent the 2 legs of that right triangle. So naturally for the distance that we're traveling right here, right, is like our hypotenuse. And so we're just doing basic Pythagorean theorem to solve for z, the hypotenuse, right? And because it represents a length or a distance, they always want to view that as a positive number. So that's why they throw this into absolute values. So that's what you're seeing right here. So just some basic stuff that we've already seen up to this point. So polar form of a complex number. So again, z represents this point as a whole. So however far you went on the real axis and then however far you went on the imaginary axis creates that point, right, that we would see as an ordered pair. That's what we're seeing in this diagram right here. If we did want to write this in polar form, as always, whatever you're doing left and right is like your x value. We represent that with our cosine of theta. Whatever you're doing up and down is your y-axis value. And so we represent that with our sine of theta. And we worked plenty on that in our previous lesson with this type of idea. And so that should look pretty familiar to you guys. Obviously, the r applies to both of those guys. We learned in our previous section that our cosine theta is the x and our sine theta is the y, right? And so we're just laying that out again right here in this look. So again, still a lot of familiarity here. Still know that the radius here is still, again, just Pythagorean theorem with our right triangle. tangent is still sine over cosine, or y over x, or in this case, b over a, right? Same thing, different letters, basically. So then again, just want to compare real quick, anytime they talk about trig form or polar form, is this guy that we already mentioned. And then if you ever see something about standard form, those are more of the Cartesian plane values, like an x and a y. Right? So those are the two looks that we're going to be working with. All right, so continuing on here, we're going to start out by just taking some terms like this that are in standard form, and we are going to convert them into trig form or polar form, really the same thing. So the first thing that we're going to need to do on this is figure out the radius, our r value. So again, going back to what we've already done before, we're just going to be doing the square root of a squared plus b squared. So if you look at this right here, guys, do notice on this that when you do b squared, b is the number in front of I. It does not include the I, okay? So do keep that in mind. So we did a squared plus b squared, and that came out to be 4, which is our r value. So from there, we need to come up with the angle that we're working with. And this takes you right back to what we just did in our previous lesson. So we can do the tangent of is y over x. So if we do the inverse tangent of b over a, and that's what you're seeing right here, that's going to help us identify our angle. So we know the angle that produces the tangent ratio of 1 over rad 3 would be pi over 6. And again, guys, all back to our unit circle. If you want, you could certainly draw right triangles to help you with this, or you could just have that kind of, especially quadrant 1 of the unit circle memorized, and that would help you find this angle as well. Anyway, moving on, so we now know the angle for this, and so now we can convert this into polar form or trig form. So remember, that was simply writing it as r cosine theta plus I sine theta. Right? That's what we just saw on the previous page. So once you know the r and theta, all we got to do is plug those in. So let's take a look at the next one here. I'm trying to give you multiple examples so you can see all the different cases you might run into. So if you look at part B, notice this one is 5 minus 5i. So again, if you were to look at this graphically, it's going 5 to the right on the real axis, and then down 5 on the imaginary y-axis. Okay, so that puts you at this point right here. So this is like point Z, right? This is what they were talking about on the previous page. So again, they're going to start out by just coming up with the value for the radius, just Pythagorean theorem. That's really all that is. That's just a squared plus b squared equals c squared, and we're getting the value for the radius. So when you do that on this one, you come out with 5 rad 2. Again, we're going to do the inverse tangent to figure out what the angle is. So we did the inverse tangent of negative 5 over 5. And so if we did the inverse tangent of 1, now the approach they took on this, and I'll kind of show you two different ways you could look at this, is they said, well, let's just find the reference angle and then figure out where are we on this unit circle here. So, I mean, it's not really the unit circle, but it's the same angles as the circle would be. So they said, let's not treat this as -1, let's just treat it as 1 so that we can just get a reference angle, and then we'll figure out ultimately where we're at on this circle. So they said the inverse tangent of positive 1 is 45 degrees, or pi over 4, but that would put you here. So instead of going up pi over 4, we're simply going pi over 4 this direction. So we could either call this negative pi over 4, or if we wanted to keep it in terms of a positive circle and go this way with it, we'd be looking at 7 pi over 4. Right? So they came up with the reference angle. So again, you can see the two looks right here. So they came out with that 7 pi over 4. Again, guys, notice on this that 7 pi over 4 is an appropriate angle, right? Because that's where we went if we were to go this way around the circle. But the way they're viewing these is, where did we go from 0, 0? Right? We went to the right and then we went down. So they want to view it in terms of this angle right here, which would be negative pi over 4. And so that's ultimately what they are putting into this answer that you see right here. Okay, so guys, the other way we could have looked at this is if we would have just said, what's the inverse tangent of -1, and don't even do the absolute values, we still could have looked at that and said, well, where do we get -1 for a tangent. I get it right here at 7 pi over 4. I also get it right here at 3 pi over 4. And obviously by looking at the graph, I know that I'm in quadrant 4, not quadrant 2. So I still would not have considered 3 pi over 4 as part of my answer. I would have looked at my graph and said, okay, I'm in quadrant 4. This has got to be 7 pi over 4. But again, the way they want us to view this answer is not as us taking laps around the circle, but rather moving left, right, up, down on the imaginary plane, right? So we did the real value, we did the imaginary value, and so they want this angle right here. So we're going to treat that as negative pi over 4 as we went from 0. Let me give you one more look. So again, if we had negative 2, negative 5i, it does help to keep in mind that you are in quadrant 3, because that's going to help you determine what angle to use for theta. Okay, so the graph really is a great way of helping you identify the appropriate angle that should go into your answer. So on this one, again, solving for r with Pythagorean theorem. So we get the root 29, and we are going to do inverse tangent of b over a, or y over x, in order to figure out the angle. Notice on this one, we had to go to a calculator for this one because 2.5 is obviously not one of our ratios that we would see on our unit circle, right? The previous two were things that we would see on the unit circle, but this one is not. So when you get one of these I don't know how would I word that, not common angles, right, that we could not pull off of the unit circle, then we're going to need to use a calculator to do this in radians instead of leaving it in terms of pi. So that's what they did here, is they said, well, let's just do the inverse tangent of 2.5. They come away with 1.19. Here's where you got to understand what quadrant you are in order to write your answer, right? 1.19 would put us right here, right? So if we just looked at that as 1.19, we have to understand that that's just our reference angle. So this right here is 1.19 radians. So that's the reference angle. So here's where we have to understand what quadrant we are in. So how do I show this angle right here? Right, so if this is my reference angle is 1.19, then essentially I am going from pi plus 1.19 give us, this is our angle, right? So really 4.33 is theta. So we are viewing that from here, from 0, to get that angle. So 1.19 was just the reference angle. We want to view that as making sure we're using the appropriate angle to place us in the right quadrant. Guys, along those lines, let me just mention this. Something we talked about in an earlier chapter that I still want you to remember. So if you look back on this one, would it have been wrong to put 7 pi over 4 here? Definitely not, right? Because these numbers repeat themselves every 2 pi, right? These go on and on forever. So to put 7 pi over 4 right here is not wrong. But what we understand is, remember, all this goes back to, what do I get in my calculator from a 1-to-1 function when I calculate these answers? And we looked and we said, well, if it's positive for tangent, if it's positive, it's going to go right here. And if it's negative, it's going to go right here, right? That was the values that we would get in our calculator within the 1-to-1 function. So those are the initial values that are presented to us. Now, if I take this answer of negative pi over 4 and I add 2 pi to that, I get 7 pi over 4. And I'm still in the same location. So to say 7 pi over 4 is not wrong. It's just not the initial angle that would be presented like from the calculator within the 1-to-1 function. Okay, so but if we added 2 pi to that and called it 7 pi over 4, that's not wrong. You could add another 2 pi to that and give it that angle, and that's still not wrong. But just so that we're all putting things in common terms, they kind of want us to strive for the initial angle that we should be using if it's within one of those quadrants. So hopefully that helps, but let me know if you run into issues within the assignment, and we'll definitely clarify those type of things. So again, you can see the way they wrote the answer for that. Let's practice one. So if you want to give one a shot, go ahead and try number 4 here. So I'm looking at negative 4 plus 8 root 3i. And the I is not under the radical, technically. So you can see that as 8i root 3. Always helps to kind of view this in terms of what quadrant we are in. So if I went left 4 and up 8, or 8 root 3, so left 4 and up 8 root 3, I can see that would put me in quadrant 2. So that's just something we're going to keep in mind here. All right, so let's find out the value for r. So if we did our Pythagorean theorem, so a squared plus b squared, so let's see, 64 times 3 would be 192. So if I add those guys together, it looks like 208. And we are expected to simplify those radicals whenever we can, so let's do that. So we could see this as 4 root 13. So there's our value for r. Now we got to come up with as our angle. And so this is where we do the inverse tangent of b over a. And again, this is where they were saying, you know, you could treat this as a positive 4, just identify it as a reference angle, and then go from there. So we could kind of take a couple approaches here. I'm just going to take kind of the straightforward approach of saying that was negative 4. So if I clean that up, I'm looking at negative 2 root 3. And the first thing I want to look for is that a value on our unit circle, right? If I look at tangent ratios on the unit circle, could I get that? Am I going to see that within our unit circle angles? And that's not a value that we would be able to come up with. So let me just hit the inverse tangent of negative 2 root 3. And I get negative 1.29, we'll call it. So again, guys, recognize what that's giving me here. Negative 1.29. Remember, in the calculator, if it's positive, it would go here. If it's negative, it would go here. So what they just gave me was my reference angle. So I went downward 1.29, right? And so that's my angle right there. But again, I can tell by with a graph that this tangent is in quadrant 2, not quadrant 4, right? So to identify this, I would want to add pi to this in order to get the angle in quadrant 2, which is 1.85. So our angle, which would be this one right there, is 1.85. And that's going to be our theta, so now I can put all this together. Guys, again, looking at this, one thing I always want to take into account is information like this. So they said make sure that your angle is between 0 and 2 pi. So even though, remember, I mean, this same angle I could get by going this direction, in a negative direction. And it's not wrong, it's just a different way of looking at it. So then they give specific directions like this so that we're all putting it in common terms. On the previous example, on the previous page, when I said, you know, it's not wrong to say 7 pi over 4 instead of negative pi over 4, they really mean the same thing, but there was no domain given. So really either of those answers would be accepted, except in order for us to all at least try to view it in the same way, they want us to give the initial value if there's no domain given. But that problem could have just as easily has said, give your answer in terms of 0 to 2 pi, right? And so if they had provided information like this, we would have used 7 pi over 4 instead of negative pi over 4. So anyway, pay attention to those little details. So to finish this one off, we're going to put this in terms of r. And then we got our cosine theta plus I sine theta. Barely got it in there. Okay, so that's converting into trig form, or polar form looks like this. All right, so how do we multiply complex numbers? I'll show you real quick as something out of your book. So this is a chart on page 497 just to help you understand what it would look like to multiply z values. So that's what we were just finding, right, was z values. In terms of our cosine theta plus I sine theta. Those represent z values. So what if I had two different z values, like this one? So here's the first z, and here's the second z. So how do I multiply those together? And this box also shows us how we would divide them. So if I were to multiply two z values together, I'm going to multiply the two r values out front. Inside these brackets or parentheses, I'm going to find the cosine of the sum of the angles plus I times the sine of the sum of the angles. Guys, this all goes back to thinking about rules of exponents. And keep in mind, whenever you multiplied two terms together, remember the rule was to add their exponents together. And so we are adding the angles here, and we are adding the angles here. If you think about this in terms of division, well, what did we do with the exponents when you were dividing? We subtracted the exponents, right? So you can really kind of link this to the same rule. So when you're dividing, you'll divide the r values, but in terms of the angles, we're going to find their difference. Right, and so that's kind of the path that we're going to be following on these. So here's the one they did. They said, let's multiply the first z times the second z. So when they did that, they did this r times this r. So that's the look that you're seeing right here. On the interior, they are adding the angles for cosine and for sine, and then we just simplify these as much as we can. So within these, you'll often get angles like this that are not on the unit circle, and so I can't figure out the cosine of negative pi over 12 from like my unit circle knowledge, so this is all going to be straight calculator stuff. So from here this is now in terms of like a plus bi, right, because they said write this in standard form, and as we saw in my very first page of notes, standard form is a plus bi, right, and so that's what they're trying to put this in terms to. So they're multiplying this guy times this in their calculator in radians to get the a value, and then they're multiplying this times this guy in their calculator to get the b value, right? So then they're putting that like this in standard form. Let's take a look at this guy. We're going to try one of these together here. So something we're always got to pay attention to, guys, is when you look at the directions, pay attention to what form they want you to write the answer in. Like if it says trig form, we got to follow those directions. If it says standard form, like the one that we just did, we got to follow those directions. So always try to read careful for what they're telling us here. But if we're going to multiply, we're going to start by multiplying r times r. So rad 2 times rad 3 would be rad 6. And then on the inside, we're going to have the cosine of the sum of the angles. So my cosine sum is 3 pi over 4 plus 2 pi over 3. So we're going to use that to get our cosine value. And then let's do the same thing with our sine values. We're going to add the angles together. All right, so there is our setup. And really, one thing I wanted you to see on this is, what if when I add these together, I get an angle that is on the unit circle, so I could figure out without a calculator. So if possible, let's see if we can simplify this by hand. And again, if you run into an angle that's not on the unit circle, then we would use the calculator for that. But otherwise, if we can leave it in terms of pi, then we're going to do that. So if we created some common denominators here of putting these over 12, so let's see, what would that be? This would be 9 over 12, and this would be 8 over 12. So add those up, and we got 17 over 12. And that, of course, is not a unit circle value, so I'm going to leave this as the cosine of, oops. cosine of 17 pi over 12 plus I sine 17 pi over 12. And so we'll leave it just like that. If this was a unit circle value that we knew, we could simplify this, right? But as far as this is concerned, we're going to stop right there because it says trig form, and that's trig form. So I'm going to leave it just like this. If it said standard form, then we would do what we did on the previous problem, and I would distribute the root 6 and do all that in my calculator to put it in decimals. So what about dividing? So you guys also saw on that same box on page 497, the path for dividing, very similar. But now in this case, if I'm going to do z1 divided by z2, right, they're going to start by dividing the r values. So they're going to do 4 divided by root 2. Which we could, of course, simplify that. Since this is going to go into standard form anyway and go into my calculator, I'm not going to bother with trying to rewrite that guy right now. It's all going to go in my calculator anyway. So we got r divided by r on the outside. On the inside, we know we're going to be finding the difference of our angles because it's now division. So in my cosine, we're going to do our z1 minus z2 angle, so pi thirds minus 5 pi over 4. Plus, we have our I sine, and again I'm going to find the difference on those guys, which is still pi thirds minus pi over 4. And so that's going to be our setup. Really the rest would be calculator if they want this in standard form. If these are not angles that are on the unit circle, if they are, so like if you look at this one, so here was their work. So they're just doing the same thing I was just showing you guys. So that was the setup I wrote on the previous page. They took it one step further and combined fractions. In this problem, they left it in trig form, even though their directions specifically said standard form. So really on this one, if we wanted to convert this to standard form, again, this is all going to be calculator. So you would distribute that. This is going to be one number as a decimal. And then if you also multiplied this by 2 rad 2, you'll get your b value as a decimal. And we would write it as a plus bi. So anyway, I have one more thing to show you to finish off part 1 of our lesson here. So take a look at de Moor's theorem. So de Moor, one of our famous old dead mathematician people. And this theorem is going to help us with raising z to an exponent. So we already looked at how to multiply and divide them. This theorem is now going to help us with exponents. So one thing that I would again link this back to is think of your rules of exponents. Whenever you had a power raised to a power, what was the rule? The rule was to multiply the exponents together, right? It went back to, like if I just gave you something basic like this, x to the third squared, right? A power raised to a power, the rule was to multiply those exponents, right? So similar idea on this. I got now z raised to a power, so now notice, now my angle is being multiplied times n, right? And so maybe that will help if you kind of link this back to your rules of exponents. Maybe that'll help you remember what operations to use within this. So as you look at this, if z represents that look right there, and I do z to some power, so I'm raising this whole thing to the power of n, right? So it really looks like this. So when you say z to the n, what you're really saying is all of this to the nth power. So here's the way we lay this out. The r gets the exponent, so r to the nth. And then again, we're going to multiply n times theta for the angles. So there's the layout right there. One of the issues on this, though, is what if I'm given a problem in standard form rather than trig form, right? Because with de Moor's theorem, it goes back to working with trig form. So we have a little extra work to do on this one because before I can even apply this theorem, I have to have my problem written in trig form. So that's going to be the first thing that we do. So here's what we started out the earlier lesson with, is let's just first convert this into trig form. Okay, so just look at the parentheses for a minute. We're going to start by solving for r. I'm a little concerned I'm running out of room, but I think I'll be okay. So I'm going to start by solving for r. Remember, that's Pythagorean theorem. So I'm doing a squared plus b squared, and that would just be 3. So square root of 4, a nice easy r value of 2. How do we find the angle? Remember, that was inverse tangent of b over a. So rad 3 over 1, which is rad 3. So if we said what's the inverse tangent of rad 3, or what angle produces the tangent ratio of rad 3, we would get pi thirds. And again, guys, consider what quadrant we are in right now. Based on this, I'd be going right and up. So I know I'm in quadrant 1, which means I get to keep pi thirds as my answer for theta. So let's lay this out in terms of trig form. So we have our r. I'll give it the full value here. So z equals r times cosine theta plus I sine theta So now that we've put it in terms of trig form, now I could apply De Moivre's theorem and raise this to the third power. So now essentially we are doing, I'm going to do this just so I can separate this out. We're going to raise our z value to the third power. So I'm taking all of this and raising it now to the third power, because that's what we were ultimately being asked to do with this. We just had to get it in the proper form before we could apply the theorem. So let's just go straight on into this theorem. We're going to do r to the nth power, so 2 to the third power. And I'll just lay this out for the sake of notes. We know that's 8, but I'll simplify it on the next step. On the inside, I'm looking at cosine of n theta, so cosine of 3 times pi over thirds plus I sine theta, which is also 3 times pi over 3. So there's just the application of De Moivre's theorem, and now we're going to clean that up as much as possible. So we know 2 to the third is 8. Within these parentheses here, right, if I did 3 times pi thirds, it's just going to be pi. So I can simplify it to this stage right here, and we can actually take this all the way down further, because we know the cosine of pi is simply, let's see, cosine pi would be -1, and the sine of pi is 0, and so that would zero out. I'm left with 8 times -1, which is -8. When all is said and done. So just simplifying that as much as we can. But again, the key step on this one, guys, was recognizing if I'm giving it in standard form, I need to start by putting it into trig form before I apply De Moivre's theorem. We're going to try one more together. So this one, again, this is given in standard form. So we're going to try converting this into trig form and then applying De Moivre's theorem. So again, first things first, we're going to do my r value with Pythagorean theorem. Let's see, a squared, so if I square this, it's going to become 2 over 4, which is 1/2, plus b squared would also be 1/2. which is 1, which the square root of 1 is 1. So there's a nice easy r value for us, just a value of 1. We need to find our angle with inverse tangent. So b over a. So if I did this over this, you guys can see it's going to be negative 1. So where's the tangent values for negative 1? Let me just quickly go back to our unit circle and remind you. So I know by looking at my unit circle that that would occur right here at 7 pi over 4, or you could say negative pi over 4. That would also occur at 3 pi over 4. So how do we know which one to use? Well, if you look at where this would go on the graph, I'm going to go left, then up, right? So this would put me in quadrant 2, which means I need to use 3 pi over 4. So there's our theta. Let's put this in terms of our trig form now. So z is equal to r, which you don't have to write the 1 there. I'm just putting it there for visual here. So r cosine theta plus I sine theta So now that we've put it into trig form, now I can apply De Moivre's theorem that we saw up above, and in this case we're raising to the 8th power. So starts out with r to the 8th power, 1 to the 8th, which again, I know you don't have to write that. 1 to the 8th is still 1. I'm just putting it so we can see where everything went within our setup here. So r to the n, and on the inside I'm going to do cosine n theta. So cosine of 8 times 3 pi over 4. Plus I sine 8 3 pi over 4. Alright, so there's our setup using De Moivre's theorem. Let's just do a little cleanup. This is where I would say, okay, obviously 1 to the 8th is 1. I don't even need to write that. Inside of these guys, I have cosine. If I multiply, that would be 6 pi. Yep, so that's something we'll definitely be able to simplify. So 6 pi is the same thing as 0, right? So essentially I'm at the cosine of 0, which is the coordinates 1, 0. So I know the cosine of 6 pi is 1. I know the sine of 6 pi is 0. And so now as I clean all that up, it's just 1.